Hello, Calculus kids. This is our first section in Calculus, AP Calculus AB. And section 1.1, can change occur in an instant is the question on the board. And so there's, from your research, I know I asked you to figure out what is calculus, who invented it, and what's it good for, who uses it. You needed to put together a bit of a little essay for me on those facts. And hopefully you figured out that there was this guy over here in England. All right, here he is. His name is Sir Isaac Newton. There's a picture of him. And he was in this is in the 1600s or so. And then you have this other guy over here in Germany. And his name is Gottfried Leibniz. Spell it right. F-R-I-E-D L-I-E-B-N-I-Z. And he's over here in 1646. And both of these guys are coming up with these crazy, interesting facts that involve calculus. But guess what? There wasn't Google, there wasn't Siri, there wasn't phones that you could, iPhones or phones of any sort. So neither one knew what the other one was doing. They were both in totally separate parts of the world, actually investigating the same facts of math. And neither one knew that the other one was doing it too. So there's a lot of debate about who actually is the father of calculus. Some say Newton, some say Leibniz, and actually they're probably both right. I guess by the dates you would say that Newton started it more, like was the earlier starter, but again there's great debate over that. So you'll see as we go along, sometimes there's notations that became the traditional notations for AP Calculus, for calculus itself, that are Newton method ones, and some are Gottfried Leibniz method ones, like notation wise. We'll talk about that when we get to it. But anyway, more when we get to derivatives and such. All right, so here we go. Can change occur in an instant? So here's the story. Mr. Bruce's distance from his house is modeled by the function d of t. Here it is over here. While riding his bike to the store, he realizes he dropped his wallet and turns around to find it. After finding his wallet, he finishes his ride to the store. Kind of reminds me of our friend Noah. Noah dropped his earbud in the hallway and had to go find it yesterday. So he came all the way to the classroom, but had to go back and retrace his steps to see if he could actually find the earbud. And thankfully he did. So there you go. Good news for Noah. After finding his wallet, he finishes his ride to the store. What is his average speed or rate of change for his trip to the store if he arrives after 8 minutes? Here he is, 8 minutes. And you're looking at this and you're thinking of rate of change. What does the word, or do the words rate of change actually mean for us? And actually they mean slope. Anytime you see those words, rate of change, average rate of change, any of that type of thing, you're going to think slope. Well, let's go over here to the margin and let's talk slope. Oh, can't see my margin. Hang on, let me see my margin. Slope. Okay. So, back in the days of Algebra 1, and you talked about slope, you know that the official, well, maybe you know, the official equation for slope is y2 minus y1 over x2 minus x1. Just like back in the day. A lot of times kids get confused. They say, well, should the x's be on top? Should the y's be on top? And I think I've shown you before that it's kind of like a picnic table. Oop, x. With martini glasses on top. Okay, so if that's the case, I want to figure out the slope for the first 8 minutes. There's Levi. Levi's saying hi. For the first 8 minutes. So what you're going to do is figure out, our function is called d of t. You want to know what d of 8 minus d of 0 is over 8 minus 0. Right? We're using the slope formula. Average rate of change. So, D of 8, I'm going to estimate. Well, where am I at 8? I'm going to estimate. Oh, I didn't even have to estimate. 1,300, they tell me. D of 0 is 0. Over 8 minus 0. And so there you go. You're just going to calculate that out. If you take 1,300 and divide it by 8, you get 162.5. And you've got to go back and think about your units. Well, the 1,300 is talking about meters, and the 8 is talking about minutes, so this would be meters per minute. There you go, his average rate of speed. What was his average rate of change between 2 and 6 minutes? Well, average rate of change is the same thing as this was. It's a rate of change. So I want to now know between 2 and 6 what D of 6 minus D of 2 over 6 minus 2 is. All right, D of 6. D of 6 is right about here. Now I'm making an estimation. I'm going to say that's 800. D of 2 is right about here. I'm going to say that that's about 1,100. Could you say something different from me? Absolutely, you could. We just need to be in the same hood. R over 6 minus 2. All right, so I'm going to divide that out. Actually, interestingly enough, it comes out to be a negative 75 meters per minute. And that makes me pause for a moment and think, negative? What do you mean negative? Like, what does that mean? So if I'm thinking about the actual logistics of that, the fact that it's negative, I'm going to put it down here. The negative means, remember he dropped his wallet? What did he do? He's going back to his house. So the negative means he's going back towards his house. Okay, so that's what this negative means for this problem. And then it says, okay, well, what's the average rate of change? Average rate of change, slope. Like each time you're looking at this, average rate of change, average rate of change, average rate of change. All of those are talking about slope. So between 2 and 3 minutes. All right, now I need to know what D of 3 minus D of 2 over 3 minus 2 would look like. Now we could calculate it out. He doesn't necessarily, if you watch the curriculum video, he doesn't make you actually do that, but let's just finish it since we did the others. I feel like it's undone if I don't. So D of 3, again, an estimation. D of 3 is in this neighborhood, let's maybe say 1,100. Did we say? We said 2 was 1,100, so let me do more than, D of 3 is a little more, so 1,150. Let's go 1,150. We said 2 was 1,100 over 1. So if I subtract that, I've got 50, and that would be meters per minute. D of 3, did I do that right? D of 3, D of 2, yep, there we go. All right, so is it possible to know how fast he's going at an instant? In other words, my question is, can I figure out, and this is really important in calculus, the instantaneous rate of change? What it's doing at that exact instant. Now, so far we've had an average rate of change. I'm going between 0 and 8 seconds. I'm going between 2 and 6 minutes. It is 2 and 6 minutes. I'm going between 2 and 3 minutes. Can I figure out what it's doing for an instantaneous, at an instantaneous point in time? So give an example of how to calculate a rate of change that would give a close estimate to the instantaneous rate of change at t equals 2. So here's what they really want you to do. They want you to get really, really close to t equals 2. So what do you mean by that? I need to figure out what it's doing close to 2. So what I'm going to do is figure out what d of 2 is. I'm going to subtract away, and still thinking of the slope formula, it's still a rate of change, but this time I'm going to do d of let's say 1.999. Right, that's really close to 2. And that would be over 2 minus 1.999. Alright, so what I'm going to do is then plug in values. So, if I figure out what this equals, actually I guess that's what it wants here for the next one. So let me take that away. That would be my formula. Give a rough estimate of the instantaneous rate of change at t equals 2. So what I need to do is figure out how that all looks. So let me go back to the graph up here. You can see the graph. If I take a point, what I'm going to do is, well, let me tell you what I'm going to do in this. I'm going to use a tangent line slope. So I'll show you what I mean. Use a tangent line slope. All right, go to my graph. I'm going to put a point at 2. I'm going to put a big old point here at 2. I'm going to take my ruler. Look, it's pretty pink. I have pretty purple. Purple ruler. And I'm going to make a tangent line at that location. Now tangent, do you remember secant versus tangent? Let's go back to geometry. Tangent line is a line that intersects the graph in exactly one point, tangent line. If I were to intercept it in 2 points, see how this one now, my ruler's changed, I've got 2 points, that's a secant line. So two different things, tangent line that we're going to use. Here's my tangent line. I'm going to draw a tangent line on this. My highlighter. There's my tangent line. And then I'm going to estimate what this thing is. So if I'm looking at my slope for this. So I'm going to look at this thing and I'm going to think my d of 2 we said was 1100. So I'm not going to change that. D of 1.99. Well, actually, if I use my tangent line idea, see how it comes down here at, I guess I could use I'm just going to use the tangent line slope for this. So 1100 is this point. If I take this point right here, that's at about 800. I can pick any point I want. I could go up here and pick a point up this way. That would be maybe 1300 at 4-ish. I could do that too. So it doesn't matter which ones you pick. We're just picking from the tangent line. So my slope of the tangent line, I'm picking this point and this point. So I would have then over 2 minus 0. All right, if I look at this, this is 300 divided by 2. That gives me 150. Think of your units. We said before it's meters per minute. That would be my estimation of the, oh, you can't see me, hold on, of the instantaneous rate of change. So it's coming off of the tangent line rather than coming off of points on the graph. So a little different, a little bit unusual. For number 2, now they give me a real life kind of situation. B of t represents the buffalo population in the United States, where t is measured in years since 1800. Since 1800. Now they give us equations and they want us to figure out what they represent. So what does B of 90 represent? Well, t is measured in years. You see how this is B of t. That means t must be 90. That's our time. So if I put this into English as to what we're looking at started in 1800, 90 years later, I'm now at 1890. So in 1890, in 1890, B of 90 represents the number of buffalo. Is this the only way you could say it? Absolutely not. You could say that B of 90 represents the number of buffalo in the U.S. in 1890. There's different ways you can represent it, but ultimately our meaning should be the same. All right, what does this look like? It looks like a slope formula. What do slope formulas represent? They represent rates of change. So let's think about this. This one represents the rate of change between 0, 1800, and 1850. That's what I want to say. So what does this represent? The average rate of change of buffalo population per year from 1800 to 1850. All right, slope formula. This one's slope formula too, but do you see how it's 30, your numbers are 32 and 31.999? Isn't that kind of like what we were talking about up here at the instantaneous rate of change? And so here's what this guy is. This guy is an estimate of the instantaneous, or actually you don't need the word instantaneous, but this one is an estimate of the rate of change of buffalo population per year. Probably need to, oh no, you can still see me. Per year in the exact year of 1832. So where this is a time frame in this last one, this one is at the exact year 1832. So they're trying to get you to think about what instantaneous is versus average at the exact year versus over a time span. All right, a couple more problems from 1-1. We are going to look at number 3. So practice problems. See all the practice problems here, they start. We're looking at number 3 together. I've got the number of people who have entered an amusement park is modeled by this function E, where E of t gives the number of people in thousands who have entered the park, and t gives the number of hours since 10 a.m. For time, this is the time, between 0 and 11. The graph of the function E is shown to the right. First of all, draw a tangent line at x equals 3, or t equals 3. So here I am, here's 2, here's 4, here's 3. I need to draw a tangent line. So again, I'm going to take my handy dandy purple ruler and draw a tangent line. So here it is. Here's my tangent line. Okay, number 3A done. Number 3B, give a rough estimate of the instantaneous rate of change at t equals 3. Rough estimate. So now I'm looking at my tangent line, and you see how the tangent line goes through. You can pick any 2 points that you want that go through perfectly or somewhat perfectly through this location. So I'm going to pick, if I were to pick up here, see how 1015 looks good. So this is my 1015. That's a good point. And then I have a point, I'm going to say that this point here, the coordinate is 3, 4. Can you find the slope between them? Because that's what the instantaneous rate of change is between those points using the tangent line. So I'm going to have 15 minus 4 over 10 minus 3. Gives me 11 over 7. If I were to divide that, that would be like 1.57. Now here's what they say in the problem. This is a little tricky. They say the number of people in thousands. So 1.57 really represents 1,570 people per hour in that park, entering the park. So you might say, yo, Wenner, I didn't want to pick those points. I want to pick other points. And that's perfectly fine. You can absolutely do that. But you do want to try to pick points that go directly through. I mean, you don't want to be estimating things. So, like, pick something that's as perfect as you can get going through the coordinates. But yes, you could get pick other points, and you should get an answer similar to what I've gotten. All right, give an example of how to calculate a rate of change that would give a close estimate to the instantaneous rate of change. Guess what? All you have to do is set up, give an example. They do not want you to solve it. Just figure out the example. So give an example for an instantaneous rate of change close to 6. Well, guess what? You're going to take, what's this function called? E? E of 6. You're going to subtract away E of something really close to it, like 5.999 over 6 minus 5.999. That's all they're asking you to do. You don't have to do any more than that. All right, we're going to flip to number 6. Number 6 comes next. This is the last one for section 1.1. Then we'll look at 1.2 real quick. So in a country where the number of, we don't want deaths. Who wants that? We're not looking at that. We're going to look at births. In a country where the number of births in a year can be modeled by D, where D of T is the number of births, and T is the number of years since 1950, what does D of 40 represent? What does this represent? And does this look familiar? It looks a lot like the last question, right? So think about what your answers are. See if you can answer them. I'll answer them, and then we'll see if we match. So what does D of 40 represent? Take a minute. Tell me what it represents. Number. All right, let's see how you did. 6A, the number of births in 1990, because 40 more than 1950 is 1990. Here's your average slope, your slope. The average rate of change in the number of births per year between 1960 and 1970. So this would be 1970, 1960, 20 plus 1950, 10 plus 1950. This one now, look at how you're looking at it's exactly the year where it's 49. 49 years since 1950 is 1999. And so this is an estimate of the rate of change of births per year in 1999 exactly, at that instant, that exact place. And that, my friends, is section 1.1. So we're going to go to 1.2 real quick. Hang on. Pages are out of order. Here we go. This is something that we talked about back in pre-calc, so I don't know if you remember this or not. Section 1.2, defining limits. Again, in your study of what is calculus, you should have realized there's three main components that make up calculus. The first one is limits, the second is derivatives, and the last is integrals. And they are all super duper interrelated. So, section 1.2. The big thing in here is for a limit, and again, we talked about this back, if you remember it, in pre-calc. As x approaches, this is really good, this is really important, as x approaches, in this case, 2. Y, remember f of x is equivalent to what the y value is, approaches, what's the y value doing? The limit as x approaches 2 has a y value of 1. You're looking at this location right there. And so, looking at this, the limit as x approaches 2, the y value is 1. That would be what my limit actually is. It's asking you, what's the y value? Remember f of x? F of x is just saying what's y. When I'm at 2, what's my y value? What's it approaching? All right, what is f of 2? Well, what's the exact coordinate there? And in this case, there's really a coordinate right there, and the coordinate is 1. Now they're going to change up the picture on you for the next couple. This one means the same thing. The limit as x approaches 2, what's the y value? And so I look at that and I say, there is no y value. Well, the coordinate for this at 2 doesn't exist. This guy is a DNE, does not exist, or sometimes we see that as undefined, whichever way you like, they mean the same. The coordinate doesn't exist, but guess what? The limit does. And the limit does all because of this word approach. As I come at 2 from this direction, and as I come at 2 from that direction, do they approach the same y value? And the answer is yes. So, it's 1. So you see the difference between limits and coordinates. For limits, it just has to be what it's approaching. And for coordinates, it has to actually equal that point. All right, last one. Here's a new picture. Let's go to the coordinate first. F of 2. Well, F of 2 has a closed circle up here at 3. So the actual coordinate's at 3. However, if I go to the graph, as I ride along the graph and come at 2 this way, come at 2 this way, they both approach a value of 1. And so they're trying to show you the difference between what a coordinate does and what a limit does. Limits are approaching. Do they approach the same y value? Even if they don't equal it, that's okay. It just has to approach the same y value. Now this picture is going to give us all sorts of crazy stuff to think about. So, here we go. I'm looking at 1. Here's 1. If I come at 1, now you have to come at it from the left and from the right, and it has to approach the same y value. So I'm going to be doing some erasing here. I have an erasable pen. But as I come at 1 from the right, from the left I should say, and 1 from the right, these two, do they approach the same y value? And the answer is yes, at -1. So your answer is -1. Yes, the limit exists. Take that away. And you see how number 2 now says, okay, well, what's the coordinate? There's a difference. This f of -3 doesn't have the LIM with it. So that -3 is just saying, all right, well, what's the coordinate at -3? So I go to -3, the coordinate is 0. It's the closed circle guy. Closed circle guy is 0. Let's go through and do all the coordinates first, because they're easy. F of 2, go to 2. Where's the closed circle? Well, it's at 3. F of 1, where's the closed circle? Oh, there is no closed circle. It does not exist. Ain't no closed circle at 1. -2, where's the graph, or where's the closed circle? Well, that's at 2. And then the rest are limits. Okay, so let's go to the limit, guys. If I'm at 2, now you're looking at the graph. The fact that there's this floating closed circle, you don't really care. You're looking at the graph. As I come at 2 from the left, as I come at 2 from the right, do they approach the same y value? And the answer is yep. So your answer is 2. Take that away. Number 7, 0. Ooh, interesting. So as I come at 0 from the left, I'm going this way. As I come at 0 from the right, I'm going this way. Yep, they've got the same y value at -2. For 8, -3. All right, well, -3, looking at the graph, not the crazy closed circle there. As I come at -3 from the left, -3 from the right, they approach this 1. So they are 1. So you need to kind of keep an eye. Some are limits and some are coordinates. So you need to kind of watch that with this kind of a thing. So watch for coordinates versus limits. Because remember, for coordinates, it has to equal the y value, wherever that might be. And for limits, it just has to approach the same y value from the left and right. Number 9, give an interpretation of this statement. Well, as x approaches seven, f of x, your y value, approaches 10. That's what it means. Oh, you can't see me. Hold on. I'll show you. Alright, so a limit does not tell us the value of f of x, in other words, what the actual y value is. It just tells you what the function approaches. Right? We saw that in those examples above. So true or false? F of 1 equals has to be the same thing as, in other words, the coordinate at 1 has to be the same thing as what the limit is in all cases. And the answer is no. Like an example of that would be this guy right here. The limit is 2, because that's what the graph does between going from the left and right of 2, but the coordinate is up here at 3. So they're not the same thing. True or false? This guy's false. Not happening. F of 1, the coordinate at 1, equals the limit at 1. Well, you can take probably this one here, right? This would work. If I take f of 1, it doesn't even exist. Although the limit exists, the actual coordinate doesn't, because there's an open circle at that location. So this would be another example of a false situation. Alright, so let's try some practice problems for this, and then we are done. Number 2 is the first one. Give an interpretation of what this means. So this is your practice problem, section 1, 2, number 2. Just like we just did. So as x approaches, what's our x value that we're concerned about? Well, that's the one that the x has the arrow to. As x approaches -2, f of x, or your y value, approaches 3. Your answer right there. Quick and done. All right, next one is, actually this is the last one, numbers 12 through 19. These guys here. Now I'm going to be quiet for a moment and give you a chance to try these. I want you to try 12 through 19, and then after I do them, we'll talk about what the answers are. So you try, I try, we'll see if we match. Remember, there's a difference between coordinates and limits. I tend to like to go through and do all the coordinates first, and then go back and think about the limits, because the limits make me think, where the coordinates kind of don't. All right, let's see how you do. All right, you can pause the video if you haven't finished, and if you have, check me out, make sure I'm right. Number 12, the limit at -1. Well, approach from the left, approach from the right, you get 2. 13, I'm going to 3. 3's down here. From the left it's -1, from the right it's -1, therefore it's -1. 14's a coordinate. What is the coordinate at 2? Well, that's your closed circle up here at 1. 15's back to a limit at -2. Come at -2 from the left, it is 2. From the right, it is 2, therefore it's 2. If I take 16, the limit at 1, it is 2 from the left, 2 from the right, it's 2. 17, I'm looking at a coordinate for f of 3. Open circle, ain't no closed circles in that neighborhood, so it doesn't exist. 18, coordinate, -1. Well, that's the closed circle down here at -2. And 19 is the limit as x approaches 2. From the left is 0, and from the right is 0. Don't let that point get you all confused, because it has nothing to do with the limit. It's just a coordinate. All right, so you end up with 0, and there you go, 12 to 19. All right, so bring your questions to class or email me if you've got any. And that is sections 1.1 and 1.2. Welcome to the world of calculus, my friends. I will see you in class.